240,000 cubic meters. That is how much earth one machine removes from a hillside in a single day. Enough material to fill 96 Olympic swimming pools, one after the other, without a gap. Not a fleet of trucks and excavators working coordinated shifts. Not blasting charges fragmenting rock across a wide area. One vehicle. One continuous motion that does not stop between shifts, does not pause for weather, does not slow when the material gets harder. The machine responsible is the Bagger 293, built in Dusseldorf in 1995 and certified by the Guinness Book of Records as the largest land vehicle ever constructed. It weighs 14,200 tons. It stands 96 meters at its highest point, taller than the Statue of Liberty including its pedestal. It stretches 220 meters from end to end. The cutting wheel at the tip of its main boom, the rotating drum of steel buckets that actually bites into the hillside, measures 21.5 meters in diameter. A 6-story building spinning without pause, dragging material off the face and depositing it on a belt in fractions of a second. When you stand at the edge of the Hambach open pit mine in western Germany and watch the 293 working a face, the scale refuses to resolve correctly. The machine is too large for the brain to categorize in the usual way. The workers in high-visibility vests at its base look like figures placed there to demonstrate a mistake, clearly the wrong scale, belonging to a different image, and the hill beyond it is not crumbling or collapsing. It is retreating, steadily, in a smooth arc, as if the landscape has decided to move out of the machine's way. Before any bucket turned against rock, engineers had to solve a problem that has nothing to do with cutting power and everything to do with what happens underneath the machine. A 14,200-ton vehicle parked on soft lignite overburden, the clay, sand, and gravel that caps a coal seam, should sink. Anyone who has watched a loaded truck slowly settle into soft ground can run the extrapolation, scale the weight up by a factor of several hundred, and the outcome should not require calculation. The earth gives way, but the 293 does not sink. It crosses open fields under its own power. It navigates the sloped ramps of mine pits more than 300 meters deep. It has been driven 22 kilometers across agricultural land to relocate between mining concessions. The obvious physical prediction is wrong, and it is wrong because the engineering team made it wrong deliberately. The machine rests on crawler track units spread across its full length and width. The combined contact area of those tracks against the ground produces a ground pressure of approximately 17 newtons per square centimeter. That is roughly the pressure a standing adult exerts through the soles of their feet. The largest land vehicle on Earth presses on soft ground no harder than a person standing still. That is not an incidental feature. It is the governing constraint that determines every dimension of the undercarriage design. The number of crawler units, the width and length of each track, the arrangement of the structural frame that carries the weight through to the ground, all of it exists to keep that pressure figure below the bearing capacity of the loosest material the machine will cross. Exceed that number, and the machine stops excavating. It starts sinking into the same material it was built to remove. The bucket wheel itself works on a principle that German engineers were refining in experimental form through the 1920s and 1930s, as the first large-scale lignite extraction in the Rhineland was getting underway. A rotating steel drum carries between 16 and 20 individual buckets. Each bucket on the 293 holds approximately 15 cubic meters of loose material, roughly the interior volume of a standard shipping container. As the wheel rotates, the leading edge of each bucket cuts into the face, fills, and carries the material up and over the crown of the drum, where gravity drops the load onto a receiving belt running inside the boom. A chain of internal conveyors then carries the material back through the boom and into the central body of the machine, where it transfers to an external belt system. The external belts at a mine like Hambach stretch for hundreds of kilometers in total, routing material from the excavation faces to crushing plants and spoil piles kilometers away. The operator in the control cabin adjusts the wheel rotation rate and the angle of the boom cut to keep the belt load balanced. Too much material at once, and the belts seize and tear. Too little, and the downstream processing equipment falls below capacity. The 293 draws up to 16.6 megawatts of electrical power when operating at full output. It does not run on diesel. A heavy electrical cable follows the machine across the mine floor, connecting it to substations on the perimeter. The machine's upper structure rotates on a central slewing ring, swinging the boom in an arc as the wheel cuts from left to right across a face. When the pass is complete, the crawlers advance incrementally, and the next pass begins. After dozens of passes, the face has retreated several more meters. After a week, the difference across the landscape is visible from any elevated point near the mine edge. After a month, the topography is measurably changed. A hill is not excavated. It is absorbed. How this technology reached the scale of the Bagger 293 is a story that runs from the 1920s to the 1990s and involves several hundred design iterations across multiple German manufacturers. The earliest bucket wheel excavators in the Rhineland were small enough that an engineer could walk beside them at a comfortable pace and keep up. They grew with the energy demand they existed to supply. Each generation was larger, and each size increase forced a redesign of the undercarriage to maintain ground pressure, a redesign of the slewing ring to handle the increased torque, and an upgrade in the electrical supply to match the higher power draw. The progression was not smooth. There were machines in the 1950s and 1960s that proved unstable under specific loading conditions, incidents that killed engineers and damaged equipment, and redesigns that took years to validate before production resumed. By 1978, when the Bagger 288 was completed at Hambach at 13,500 tons, the machines had reached a scale where their operation began to affect infrastructure beyond the mine itself. Geologists monitored railway lines and road foundations in the surrounding region for vibration effects. The 288 held the record for largest land vehicle for 17 years, until the 293 came into service. Both machines are still operational. When the Bagger 288 needed to relocate between mining concessions in the early 2000s, the distance was roughly 22 kilometers across public land, agricultural fields, and minor roads. Disassembling a machine of that size and precision, transporting it in pieces, and reassembling it at the new site carries risks that can damage slewing ring bearings, calibrated sensor systems, and structural welds in ways that are expensive and slow to correct. The decision was to walk it. Preparing the route took months. Agricultural fields were reinforced with steel ground mats to distribute the crawler pressure. Temporary structures bridged road crossings. A team of engineers walked ahead of the machine's path each day, checking the soil conditions for buried drainage pipes, service utilities, and soft spots that would require additional ground preparation. The machine's planned route was modified 3 times before the crossing began. The full 22-kilometer journey took approximately 3 weeks, at an average advance of roughly a kilometer per day, with stops for ground inspections and minor route adjustments. The 288 arrived at its destination without significant damage and resumed production within days. During normal operations, the Bagger 293 carries a crew of 4 to 6 people working in rotating shifts from a climate-controlled control cabin mounted high in the superstructure. The cabin sits on vibration isolation mounts, the oscillation from the rotating wheel, the conveyor drives, and the crawler movement is constant and would be physically debilitating across a 12-hour shift without them. Monitors in the cabin display the conveyor load, the bucket wheel speed, the boom angle, and the position of the external belt connections. The operator adjusts these parameters continuously, based on what the face is yielding and how the belts are running downstream. Shift handovers happen with the machine in motion. The outgoing operator and the incoming one spend 30 minutes together in the cabin, going over the current face conditions, any changes in material hardness, any alerts from the maintenance sensors, and the planned advance for the next period. The machine does not stop. The briefing happens around the continuous motion of the wheel. Those 6 operators are a fraction of the total workforce a single bagger requires. A permanent maintenance crew of more than 50 technicians is attached to the 293, electricians managing the power supply and motor systems, mechanical fitters servicing the boom structure and slewing ring, conveyor specialists, and the rotating crews responsible for the bucket teeth. The cutting inserts, hardened steel tips on each bucket that directly contact the material being excavated, wear at a rate that depends on the abrasiveness of the overburden. In sections with significant gravel or rock fragments, a set of teeth may need replacement within days. Changing a complete set requires stopping the wheel, rigging personnel onto the boom at height, and working in whatever conditions the weather provides. In winter, in the open pit, that means working under floodlights in temperatures that can fall well below zero, on steel structure that is cold enough to require insulated gloves for grip. Unplanned downtime on a machine of this class costs the mine operation several €100,000 per day in lost output. Planned maintenance cycles are therefore treated with the same operational seriousness as production targets, and the schedule is protected against pressure to extend component life past its rated interval. A failure in the slewing ring, the large bearing assembly that allows the entire upper structure to rotate, requires weeks to repair and involves cranes brought into the pit that are themselves major logistical operations. No one runs a slewing ring past its service interval. Not everything can be scheduled against. In 2015, an unexpected stability failure occurred at the northern face of the Hambach mine. The overburden in that section proved less competent than the geological survey had indicated, and a portion of the face collapsed in a way that required the bagger operating there to halt, the area to be cleared, and the excavation plan to be revised over several weeks. No personnel were injured, but the incident illustrated the fundamental exposure that limits even the most capable machine. It operates inside a geological model, and when that model has an error, the consequences are expensive to resolve and cannot be predicted in advance by the machine or its operators. Fire is the other risk that the maintenance crews manage as a continuous discipline. The combination of coal dust, the electrical load of a 16-megawatt machine, and the lubricants required across dozens of bearing assemblies and conveyor drives creates conditions where an ignition event reaching a belt or a motor housing can develop before a manual response can reach it. Automatic suppression systems are installed in the highest risk zones. The operators carry extinguishers, and the crews on inspection rounds check heat sensors and smell for electrical burning as a routine, not as an exception. The scale of the machine means that no monitoring system can see all of it at once. The scheduled end of these machines is already written into German federal law. The country's coal phase-out sets 2038 as the final year of lignite extraction in the Rhineland. That gives the existing baggers roughly 15 more years of operation before the mines close. When they do, reclamation begins. And in the Rhineland, reclamation is not cosmetic. The excavated voids are progressively flooded as adjacent sections are worked out, creating artificial lakes. Spoil heaps are graded to stable angles and planted with forest species suited to the substrate. The process takes decades, and it is already well underway in sections of the region that were mined out earlier. Some of the lakes that now attract weekend visitors from Cologne and Dusseldorf were active open pits in the 1970s, worked by earlier generations of the same machines. The current landscape was built from the material the baggers moved. What happens to the machines themselves after the mines close is not settled. The Bagger 288 is being designated as an industrial monument and is visitable in its current location. Others will be scrapped. The economics of preserving a 13,500-ton steel structure indefinitely are difficult, and the conversation about which of these machines represent a record of human industrial ambition worth protecting the way important ships or aircraft are protected has not produced a consensus. The structures themselves do not argue for their preservation. What they accomplished is not in dispute. The Hambach and Garzweiler mines together produced, at their combined peak, more than 90 million tons of lignite per year, supplying roughly a quarter of Germany's electricity. That output rested on the bucket wheel excavators, but also on the hundreds of kilometers of belt infrastructure connecting them, the power substations supplying them, the geological survey teams working ahead of them, and the maintenance workforce keeping them running across 3 shifts every day of the year. The Bagger 293 is the most striking single object in that system. It is not the system, it is the part the cameras can find. The engineering decisions that made these machines possible, the failures that preceded the working solutions, and what it takes to decommission an industry that built the largest vehicles in human history, those threads run further than this video follows. That is what this channel is here for, going past the first answer, into the mechanism that produced it. If that is the depth you are looking for, there is more here waiting.